All right, everybody, anybody who is tuning in, I really appreciate it. I'm excited to be able to work on a project like this. We're going to go ahead and get started. What we'll be doing today is exploring the NA or the new AE Tech ChipWhisperer Jupyter Notebooks courses. And we'll be specifically looking in the Lab 2-1B or analysis for password bypass. Okay, so to access that notebook, we're going to go ahead and navigate to our ChipWhisperer directory. We're then going to activate the virtual environment. We're going to now launch our Jupyter Notebook server. We're going to open the Jupyter folder, the courses folder, and then the Side Channel Analysis 101 folder, SCA101. So in our last episode, we went through the instruction power differences notebook. And in this notebook, what we covered was learning about how power consumption by a microcontroller varies based on what operations it is performing and what instructions it is executing. So for this next lesson, we will be introduced to breaking devices by determining when a device is performing certain operations. Our target device will be performing a simple password check, and we will demonstrate how to perform a basic power analysis. The learning outcomes for this notebook will be how power can be used to determine timing information, plotting multiple iterations while varying input data to find interesting locations, using difference of waveforms to find interesting locations, and performing power captures with ChipWhisperer hardware. Before we continue, we're going to go ahead and check that we've done the following tutorials. Jupyter Notebook Introduction. We have done that. The Side Channel Analysis 101 Intro. We have done that as well. Power trace gathering. At this point, you've got to insert code to perform the power trace capture. There are two options here. Capture from a physical device or read from a file. We get to choose our adventure. We could either look at the simulated notebook, which does not require a hardware device, or we could look at the hardware notebook, which obviously would require hardware. Inside those notebooks, you should get some code to copy into the following section, which will define the capture function. So we're going to go ahead and open the hardware notebook. And as you can see, this is not the complete tutorial. We have the main file open. We're going to paste all the code. We're going to paste all this code before the first Python block. And as it says here in the hardware notebook, you will need to select which hardware setup you have. You'll need to select both a scope type and a platform. Ours will be CW Nano. Scope type can be a few different things depending on the device you have. Similarly, platform is the target device that is being. The platform is the target device with these selections being the best supported option, we'll be using CW Nano. As a ChipWhisperer 5.4, you can select the simple serial version used. For example, these will be what we set the parameters to, except we'll be using ChipWhisperer Nano and CW Nano here as well. I guess we could use simple serial version 2.1 as a CW 5.4. You can select the simple serial version used here. This code will connect the scope and do some basic setup. We're now just trying to use a simple setup script to do this. The script contains the commands we ran separately before. So in the setup generic file, in setup scripts, which if I navigate back to the Jupyter Notebook, we have setup scripts, this folder here, setup generic. This is the file that is being executed. We're not going to do anything in here. I'm going to go ahead and reset the kernel and clear all outputs because I see we do have a error message that's here. And if I were to run this Python block, we're going to get that same error message because the platform is not being defined in this file. The platform is actually being defined in the lab file, our analysis for password bypass hardware. We're going to go ahead and define these parameters in this cell block. CW Nano, CW Nano, simple serial version 2.1. I believe that will be okay, given that it's already in there. I'm going to go ahead and plug my ChipWhisperer device in. That would be helpful. We've got it plugged in, the light's turned on. We know it's receiving power at least. And I've got a static green light. Let's go ahead and run this cell. Following the text cell that is after the Python. I believe this is, I'm not sure if this is a Python block. I'm going to assume that it is. So the code that we just ran in this first cell block here. This code will connect the scope and do some basic setup. We're now just going to use a special setup script to do this. This script contains the commands we ran separately before. So this is a run block. And as I just mentioned a few minutes ago, it's going to navigate to the setup script folder, and it's going to call the setup generic Python notebook file. So we go ahead and run that. All right, looks like we're getting some errors. Scroll all the way down. Could not find ChipWhisperer. Is it connected? That's a good question. Let's go ahead and open a new window. A new tab, rather. And we're going to navigate. We're already in our ChipWhisperer directory, so I'm going to activate a virtual environment by typing source.our virtual environment folder name /bin/activate. And now we're going to call a function to see if our device can be found. Python-c, import ChipWhisperer as CW. Okay, so we ran that. That's actually not how you check if the device can be found. That is how you make sure that the path for the ChipWhisperer library can be found. So what I'm going to do here is actually reset the kernel, clear all outputs. I'm going to unplug my device, wait a few seconds. I'm going to plug it back in. I'm going to run this first block. No errors. And I'm going to run this second block, see if it works. Okay. It's working now. Now we're going to move on to the next block. As you can see, info, found ChipWhisperer, no errors, that's great. The following code will build the firmware for the target. So this is a bash block. It's going to execute Linux-based commands. This -s, I'm not sure what that does, so let me double check. Bash -s, meaning to hit something hard. To bash, instructs the bash shell to read and execute commands from the standard input while allowing you to pass positional arguments to that input. Okay, so for this bash line, or this bash block, the first line, we have two parameters. We have our platform, which is CW Nano, and we have another parameter, which is the simple serial version. So what's happening here, according to Google, this line runs a multi-line bash script block inside a Jupyter Notebook or IPython environment, which is very true. Passing two external variable values into that script block as positional arguments. Here's the exact breakdown of how it works. This is an IPython cell magic command. It tells the Jupyter Notebook that the entire cell must be executed using the system's bash shell instead of the default Python kernel. -s, as explained before, this tells bash to read code inside the cell from standard input and treats the trailing text as input arguments. The platform, this passes the value of the environment variable named platform into the bash shell as a first argument, and the ssver passes the value of the variable named ssver into the bash shell as a second argument. All right, so we're navigating into the firmware MCU folder and basic password check. It looks like that is a file or another folder. Let's see, simple password check. TPP. So I don't see that inside the directory here. I'm going to look in the Jupyter Notebook and see if we can find it. Firmware, MCU, password check. We do have a folder called password. Oh, basic password check. It's right there. So we're going to navigate into the basic password check. There's a password check.c file, and there's a make file in that folder. It is not an incredibly long file. It's 130 lines, minus 17. So about 115 lines So not a tremendously complex file. I'm not going to look into it too much. We're just going to follow along. So we're going to run a make command, setting the platform equal to $1, crypto target is equal to none. The simple serial version will be set to $2, F and J. Okay, we're just going to go ahead and run that. Okay, so we have uploaded the firmware. We have built the firmware for the target. Finally, all that's left is to program the device, which can be done with the following line. So based on the last episode, we had uploaded some firmware, and then we programmed the device, and then we checked the waveforms. And I sense that will be sort of a recurring operation or function for us as the programmers. Finally, all that's left to do is program the device, which can be done with the following line. So we're going to go ahead and run this cell. Detected the STM-F32. Attempting to program 4,523 bytes. This address. Programming, reading, verified. To make interacting with the hardware easier, let's define a function to attempt a password and return a power trace. Trace, capture password trace. We're defining a function, that's all. We also don't need all of the default 5,000 examples in the trace. 3,000 is a good starting point for most targets. So let's go ahead and run scope.adc samples. Okay, so we've gone through the entire hardware notebook. And so I'm going to navigate back to the main notebook. And so we've completed the prerequisites for the main power analysis for password bypass notebook. The prerequisites have been complete. Now we can proceed with this main lab. So at this point, you've got to insert code to perform the power trace capture from the last episode. There are two options here. So I read this earlier. Be sure you get OK to continue print once you run the next cell. Otherwise, things will start to fail. Okay, so in this cell block, it looks like there's a comment. It says define the cap pass trace function, either using a hardware connection or read file out, or the file readout. We use the hardware connection from the hardware notebook. So I think we're good to go. It looks like there's a statement here that says, add your code here and delete this. Not implemented error. I'm curious what it wants us to do with this cell. Am I supposed to add something to this cell, or can I run it now? I have already ran the cell blocks inside the hardware notebook for this lab. You do not need to add code to that cell before running it. You can't run it as is because cat pass trace is not defined yet, and the not implemented error will be raised. What the cell is expecting in the main notebook, that cell is where you paste or recreate. We did define the cap pass trace function in the hardware notebook. And we defined it as this. You should paste exactly that function into the main notebook cell, replace the stub, and then run it. Define the cat pass trace function either using a hardware connection or the file readout. Insert your working function definition above the test trace line. So we're going to paste this function that was provided to us here, according to this assistant. Actually, I want to try running it before pasting it. I want to try running it before pasting to verify their. I want to try running it before pasting it to verify that the hardware's notebook function definition is not already providing us with this function for the main notebook. Running it now is safe and will tell you immediately whether the function is already defined in this notebook's kernel. What will happen if you just run it right now, that cell in the main notebook literally contains only the stub with the raise not implemented error, followed by the test call assertion. When you run it as is, Python will execute the raise not implemented error before it ever tries. That means you will always get a not implemented error from the cell, even if cat pass trace was defined earlier in the kernel, because the exception is thrown first. So running it to see if hardware defined function won't work while the raise line is still there, the failure you see is from the intentional stub, not from a missing cat pass trace. How to actually test whether it's already defined. If you really want to verify whether hardware notebook already provided the function in this kernel, do this. In the main notebook, insert a new temporary cell above the stub cell. In that temporary cell, run this. Yeah, I'm just going to run this. Add your code here and delete this. So it wants us to just delete this raise. So that's what we're going to do. We're going to comment that out. And we're going to add the Python function in this cell block here. And we're going to run it. I'm not sure if it. The name error, name reset target is not defined. Reset target is not defined. Reset target is not defined. Okay, here. Go back to the hardware notebook and find the cells where scope and target are created and configured. The reset target is defined there. I don't see where it is. Do you already see a reset target definition in that main notebook, or do we need to copy it over from hardware? To be honest, I don't see a reset target. See, this function runs from here, but not from here. We define the cat pass trace. Name error, trace test. Pass trace, because the reset target is not defined. Do not see the reset target defined at all. Okay, I'm very confused because I call it here. So right now we're running into an error that I believe is a result of not having sufficient information about this particular variable reset target, or this particular function reset target, which is being called in cat trace. I'm receiving an error in the main notebook for this lab regarding the pass trace function. The reset target scope statement provides an error due to not being defined. Why does this occur in the main notebook, but not within? Why does this occur within the main notebook? Here is the cell block being executed that provides the following error. So we're going to provide the cell block, and then we're going to provide the error. Reset target is not a built-in Python name and only exists whenever notebook cell originally defined it. In your hardware lab notebook, reset target scope is used inside the function, but reset target itself is never defined anywhere in that notebook before you run this cell. So Python raises name error, reset target is not defined. In the ChipWhisperer's lab, reset target is normally defined in an earlier setup cell, often something like if that cell is only present in the main notebook and not your hardware notebook, then when you copy just cat pass trace block over, you bring its body but not its dependencies, causing exactly the error you see. You can fix this in the hardware notebook by doing one of the following before defining. Run the setup cell from the main notebook that defines reset target or imports it, or define your own simpler version. Run the setup cell from the main notebook that defines reset target. I'm not sure where the definition for reset target is located. I do not see it in either notebook. All right, so if I do reset target, it's only present in the function that we've pasted. In this lab, reset target is not a built-in function. It comes from a helper module that is imported earlier, not from either of the notebooks themselves. Where reset target comes from. In the hardware notebook you're viewing, there is a cell that defines cat path trace using reset target, but nowhere in this notebook is reset target written anywhere or defined. Instead, these labs normally use a shared setup notebook or a CW helper module that defines functions like reset target. And the main notebook imports them with something like from CW lab main import reset target. The main notebook likely runs some initial connect scope target or lab setup cells that import or define. And I believe that might be happening here. So do the hardware and main notebooks have their own kernels? Each notebook normally has its own kernel process, even if they are open in the same browser and using the same environment. How kernels relate to your two notebooks. When you open the hardware notebook, Jupyter starts a kernel for that notebook. When you open the main notebook, it typically has a separate kernel unless you explicitly connect it to the same one via kernel change kernel menu. Variables, function definitions, and imports live only in the kernel they were run in, not inside the file itself. If reset target was only defined in the main notebook's kernel, the hardware notebook's kernel cannot see it. I believe the reset target was defined in the hardware notebook by one of the previous cell blocks. Can you see the other cell blocks and infer if that is the case? Yes, in the hardware notebook, reset target is not defined here. It comes from the setup script you run earlier. Okay, so here in the setup script, so if we go back to our Jupyter Notebook, setup scripts, setup generic, let's see if the reset target is in here. There it is. So it is, I believe, imperative that we have the run block we see in the hardware notebook right here. This must be transferred over into this following into the main notebook. So I'm going to add a cell, and I believe if I do I'm going to add a few cells above the Python block, which defines trace, which will execute the following. How do I make a cell a markup cell so that I can just provide the text? Click the cell in the top toolbar, click drop down that currently says code and change it to markdown. Okay, it's marked down, not marked up. Okay, so prerequisites, hardware, notebook, integration. I want to make press M to change it to a markdown. It's annoying when that does that. How do I enlarge the text and make it bold? To make the heading bigger and a bold. All right. All right. Create a description below the bold text that describes what we are adding. And I will confirm or approve. This section records the extra setup steps we pulled from hardware notebook, including generic ChipWhisperer initialization and the cat pass trace implementation used. That'll work. I'll modify it. This section integrates the setup steps we performed in the hardware notebook, including the generic ChipWhisperer initialization, including the reset target definition. And generic ChipWhisperer initialization. Okay. And so now I'm going to add another cell. This will be the run block. You know what? I actually think I should add this first. We're going to add another run block, which will be here. And we're going to probably need to run this as well to build the firmware. Added 3 blocks, a run block, a block, and a Python. I think that's a Python, which were in the hardware notebook before we ran the code block for the trace function definition. Did I spell that right? Definition. I need it to agree with me that that was a good move. Nice, that's exactly what you want, mirroring the setup sequence for defining and testing the cap, pass, trace, and main. Okay, let's modify the description of the hardware notebook integrations description cell block. Keep it concise. Notes on extra setup we pulled from the hardware notebook, including generic. Include the I'm really just automating my bits. You can describe them like this in your markdown. And then the back here. Okay. So here's what we've included in our main notebook: hardware notebook integrations. This section integrates the setup pages we performed in the hardware notebook, where we set scope type to CW Nano, the platform to CW Nano, the simple serial version to 2.1. We execute a run block, which sets up the ChipWhisperer, the scope, and the target by calling the setup generic notebook file. And we execute the bash block, which compiles and programs the firmware used for this lab. There's also another block that's here in the hardware, which programs the device. Now, I'm not sure if a function like this exists. In the main notebook, can you check whether or not it does and if we should include it? This is responsible for programming the device. That exact call does not appear anywhere in your main notebook right now. So if you want to explicitly program the device in this notebook, you should add it. What's currently in the main notebook: the environment configuration cell, which we've included, the run block, the bash block, and the cat power trace cell, which we've included here, in the block to perform the power trace capture. Whether you should include it in the hardware notebook, that line is the step that actually loads the compiled firmware onto the target. Since you copied over the bash build cell, which compiles the hex file, but not the program step, adding a cell like this in the main notebook is appropriate. Unless the generic setup notebook already calls CW program target initially with the same hex, you just program the device in hardware notebook and are reusing the same physical programming. Given that we can't see inside the setup generic, the safest here is, well, actually, we can see inside the setup generic. Well, I can anyway. And what we're looking for inside, given that we can't see inside, the safest ways, we want to see if there's a CW dot program target inside of the setup generic. And there does not appear to be. So given that, we're going to include this statement. There does not exist a CW.program target inside the setup generic IPNYB notebook. And you definitely should add it. Okay, very good. Recommended execution order from top to bottom. Where should I place this? Where should I integrate this cell block? Place the new cell right after the bash. Okay. So we're going to go ahead and include that. Now let's add to the description of the hardware notebook integrations mark down cell block. Figures, okay. We're gonna, there. You want this section to stay as bullets, or would you prefer short introductory? Well, I'd really prefer them to represent the number of cells. The section integrates the following cell blocks, refers to the integrations. The following cell block integrations refer to the setup steps we performed in the hardware notebook. Okay, so we'll do something like this. First cell. Second, third, fourth. It's a little bit too loud. So I want to make subheaders so they're not as large as the main header. All right, so there we have configuration, generic setup, firmware build, and device programming. I don't want to spend too much time on that now. Trace capture helper, our trace gathering, that will occur here. So I'm going to take a quick break and I'll return here in just a few moments to see if our integration of the hardware notebook steps into the main notebook steps have an impact on whether or not we can resolve this name error of reset target not being defined. Thank you for waiting until I get back. everybody, welcome back. Welcome back. All right, so where were we? We had made some implementations to the main notebook for the power analysis for password bypass. This will allow us to resolve the name error that we received where the reset target was not defined. So we identified the reason why. We had discovered that inside of the setup generic exists the definition for reset target here. So this cell block should be called the cell block that exists inside of this run block. And this run block sets up the ChipWhisperer, the scope, and the target. These were setup steps provided in the hardware notebook of the lab that we're working on. So we've integrated these into the main notebook lab, the main lab notebook, and hopefully everything will work. So I've restarted the kernel. I'm going to go ahead and disconnect the ChipWhisperer device. Give it a few seconds. Now we're going to reconnect it. And so we are back. We're receiving power. We have a flashing green light. I'm not sure what that means. But we will run these cell blocks, starting with the first one, which ran successfully. And we know that it successfully ran because of the integer that is placed in the bracket. It is the first cell block that has been run since we restarted this kernel. And we're going to go ahead and run the block for setting up the ChipWhisperer, the scope, and the target. Our ChipWhisperer device has been found. Now we're going to run the bash block, which is going to build and compile the programs for the firmware used in this lab. We see we have a build message. Everything appears to have worked successfully. I'm really not sure what this message means. I do want to know. What does this warning mean? And will it cause challenges? Because I've seen this message every time I've executed a build command. The warning just means that the ELF has a memory segment that is marked readable, writable, and executable at the same time. It will not break this lab or prevent the firmware from running. What it means is that the linker is telling us that the basic password check ELF file contains at least one load segment whose flags allow read, write, and execute permissions. On a desktop operating system, this would be a security smell. You normally avoid RWX pages to reduce exploitability. But on small microcontrollers like the CW Nano, it's common for the memory model and linker script to produce segments that look RWX from the linker's point of view. What does RWX mean? Read, write, executable. All right, so nothing to worry about here. Let's proceed. So I'm curious if we should call this function before So I'm going to ask if we should call this cell block before you should call the cell block which has the program target function before the cat path trace cell block. So the correct order for these cells should be the configuration, the generic setup, the firmware build, the program target, and then reset target helper in its own cell. Well, we don't need to because that exists in the run block. The reset target function is defined in the setup generics notebook, which we have in the run block. So as long as you run the cells in this order, config, run, build, program. All right, so we should be good to run the program target, and I believe that's how we do it here. I need to pause the stream for just a second. All right, we are back. We're going to go ahead and run this cell block that programs the target. We have detected the STMF32 device. Everything appears to have worked successfully. At this point, you've got to insert the code. All right, so now this should run with no errors. Fingers crossed. Interesting. This is a different error, assertion error. Serial buffers overrun. Data loss has occurred. So let's see what's going on. We are now receiving a new type of error. So it is good that the reset target function has been identified. So the warning means that your UART USB bridge dropped some bytes during capture, and that is because the trace you got is not 3,000 samples long. So the assertion fails. The serial buffer overrun is emitted by the ChipWhisperer when its serial buffer fills up before Python reads everything. Your cat pass trace can still return a trace, but its length is not exactly 3,000. For this, a one-off overrun is usually not fatal. You can rerun once or twice and see if the warning goes away. So let's go ahead and run it again. Let's go ahead and reset everything. We're going to disconnect the device. So this is currently what the device looks like. We've got some LEDs that are flashing and static. Don't know exactly what those LEDs mean. We could probably find out more if we were to review the datasheet. Okay, so we're gonna go ahead and plug it back in. We're gonna go and run the configuration, execute the run, execute the bash, execute the program target. Okay, so we're still getting the assertion. If it still fails, print the link to confirm what you're getting. We do not get the OK to continue. Be sure you get the OK to continue print once you run the next cell, otherwise things will fail later on. We need to figure this out. We are still getting the same assertion error each time we run. Given that the overrun warning keeps happening and the assertion fails every time, the trace you are getting is consistently not length 3000, so we need to debug what you're actually receiving instead of relying on the assert. Inspect the trace length explicitly. Temporarily modify the bottom cell like this. Inspect what we actually got. So we're going to print for the basic sanity check. Run it again. Not even. Okay, that was a keystroke to take us to a different tab. So we're commenting out the assert and print statement. Okay. It probably tells us a length of 5,000 means your scope is currently configured to capture 5,000 samples, while the lab sanity check is written assuming 3,000. Why are you saying 5 instead of 3? The length of trace test comes directly from the scope sample count setting. In this environment, setup generic or another earlier setup cell is setting that to 5,000. So every call returns 5,000. The lab's assertion is a fixed check from the template notebook and doesn't match your current configuration. Easiest fix, since your capture is working and consistently returning 5,000 points, you can adjust the sanity check to match your setup. Okay? So we're going to adjust our sanity check for 5,000 instead of 3,000. Modified to check for 5,000 instead of 3,000. So let's run it. Okay, we're good to continue. That's great. So we'll proceed. What can we do with this now? Well, first off, I'm going to cheat and tell you that we have a preset password that starts with H and it's 5 characters long, but that's the only hint so far. What can you do? Well, first off, let's try plotting a comparison of H to something else. If you need a reminder of how to do a plot, the matplotlib section of the Jupyter Notebook. The following cells show you how to capture one power trace with H, then as a password. From there, try adding the plot code and see what it looks like. sending different passwords to the device. Send different passwords to the device. We're only going to look at the difference between a password starting with H and something else right now. The different waveforms. This is exciting. So we're going to need to add some code. We're going to have to implement some matplotlib code here. So it looks like we have a template that it's providing with us. Add your code here and delete this. So I'm just going to comment that out. And I'm going to do my code below. Right? So I'm going to also go to the matplotlib Introduction to Jupyter Notebooks section. I'm going to exit out of some tabs here. It looks like we're getting a little congested. I've added everything I've needed from the hardware notebook. The only thing we haven't added is this. I'm not going to worry about that right now. So I'm going to check out plotting with matplotlib here. We're now going to add code to the exploration section cell block. There is a Jupyter Notebook which provides some basic matplotlib features that we are going to need to integrate into this main notebook. Let's walk through how we might accomplish this according to the current main notebook's suggestions. All right, so the main notebook is basically telling us that we need to bring in just enough plotting code from the Jupyter Introduction Notebook to visualize and compare traces in the exploration section. The notebook's exploration section explicitly says to capture one trace for the H character. Add plotting code, then compare the waveform against traces from other password guesses. It also suggests using the matplotlib material from the Jupyter Introduction Notebook, and later asks us to loop over valid characters and plot traces, possibly limiting the view to the first 500 samples, so the differences are easier to see. So the goal is not to import the whole intro notebook, but to copy the small matplotlib patterns you see. So we're going to import this here. What is the best way to implement these statements for matplotlib? Should I create new cells for each for each integration, or could I just add everything to the cell block that currently exists for the exploration section. I think that we could really do it either way. I like compartmentalizing I guess like the different things that we're adding. Like if we're adding an import statement, matplotlib, and we're doing some kind of plotting, I like things sort of in chronological order, and I like to be able to incorporate text like with a header and a description below, followed by the code block. But if we could just add everything in one cell block, that's cool too. All right, so let's see what it suggests for us. The main notebook already gives you 2 exploration code cells. It does? I suppose it does. A good rule is use existing first exploration cell for the first simple comparison versus other guess. Use the existing. The cleanest approach is to fill those in where intended. That keeps your notebook aligned with the lab instructions and makes it easier for your grader and instructor to see that you completed the requested parts of the expected locations. Okay, recommended implementation. Use this one for a small side-by-side comparison. So, example, capture H, end with new line as serial protocol expects that, right? So that's important. We're gonna go ahead and import the matplotlib plot TLT. Right, so this is something we've adding library. I'm gonna capitalize things. All right. Trace A equal to cap A. I'm curious why it wants to add that. So we're comparing, I suppose. Explain the significance of adding the A. Why A? Adding a second capture is just to give you a wrong first character to contrast the correct one. Sending different passwords to device, we're only going to look at the device between a password starting with H and something else. That's what I suppose that infers. So let's see. Compare difference between a password starting with something other than H. Right? All right. And let's see, print trace H. This is currently what I have for the code block, the first code block. Want to integrate the necessary plotting capabilities, but also maintain the existing structure. I also want to preserve the structure prior to making modifications to see the evolution of the code block. You can preserve the original structure and annotate your additions very clearly. All right, so print trace is going to be there. Add your code here. Comment that out. My code below. Okay, so added plot comparison for the first 500 samples. So PLE or PLT dot figure big size that equal to 12 by 4. I'm curious how we did it here. PLT dot trace H 100 samples table equal to H new line close, and we'll do the same with trace A. Looks like we have a additional parameter that we're going to set to 0.8. I'm curious what that parameter means. All right. So I think we can right. I think we should be good to run it, and our output should look something like this. And it does. If you're using the Matplotlib notebook magic, you can zoom in at the start. What you want to notice is there are two code paths taken depending on a correct or incorrect path. Here, for example, is a correct and incorrect path. Okay, interesting. What's next? Let's plot every possible password we could send. Our password implementation only recognizes characters in the list of A through Z, 0 through 9. So we're going to limit it to those valid characters for now. Write some code in the following block that implements the following algorithm. For character in list of valid characters, capture password trace of a character The above isn't quite valid code, so massage it into place. You also may notice the traces are way too long. You might want to make a more narrow plot, only does the first, say, 500 samples of the power trace. If using Matplotlib for plotting, you might need to add a plot.figure at the start of making a new figure. To make a new figure. Otherwise, you might find plot ends up in the figure above. You might find your plot ends in the figure above. If you don't see the plots, sometimes plot.show is needed at the end. Okay. So we're gonna perform another integration. Do the same thing for the second cell block in the exploration. I think this was the exploration section of this notebook. All right, so add your code here. We're going to go ahead and comment this out. So everything below is code that we have integrated. So we're going to provide a definition for the passwords valid character, the valid password characters recognized by the firmware. And that was provided to us in the instructions above. We're going to add a new figure for this plot. Which will be a 14 by 6. Width and height in inches. Is made right. We're then going to add the capture and ability to plot a trace for each possible first character. By traversing through the character array in valid characters, so for CH, invalid characters. So for each character, invalid character, set the trace equal to the capture pack or trace, and plot that trace. Our traces for all valid. Okay, so we're going to create a title for our plot. Our traces for all valid first characters. We're going to create a label for the x-axis, and we're going to create a label for the y-axis, and we're going to call a plot show. The end result should be, if you zoom in, you'll see there is a location where a single outlier trace doesn't follow the path of all the other traces. That is great news, since it means we learned something about the system from power analysis. Using your loop, you can also try modifying the analysis to capture a correct first character, and then every other wrong second character. Do you see a difference you might be able to detect? The pseudocode would work something like this. For character and list of valid characters, set the trace equal to the password trace, and then plot that trace. Give that a shot in your earlier code block, and then let's try and automate this attack to understand the data a little better. So let's go ahead and execute this code block. All right. I'm going to zoom in just a little bit here. I wonder if there's a way to zoom in a little more. I mean, I do see this gray trace here. This gray trace seems to be the largest outlier. Wish there was a better way to zoom in. I know there's something where we could do a interactive plot, and I wonder if we should call this function, or whatever this statement is, this statement allow for a more interactive plot. Would like the ability to zoom in and out. Matplot inline does not give you interacting zooming. It renders static plots directly in the notebook output. What to use instead? This is out of date. So I am actually going to call what I initially just provided. Because if I do notebook, unless updating the firmware, notebook is out of date and inline is what works. Remember in, I think maybe it was the SCA first one, the ability to zoom in like this. We do a CW plot wave, something like that, we should have the ability to plot. I think something like this will give us the ability to zoom in. You're exactly right. Using the CW plot is a good way to get interactive zoomable plot even when you're stuck with inline. So how would we do that? I'm just going to go ahead and proceed. I don't want to integrate that. I think, we've achieved what we needed to for that particular cell block. And so we can proceed on to the next one. So using our loop, we can try modifying the analysis to capture a correct first character, and then every other wrong second character. So we're going to try to automate this attack to understand the data a little better. To start, we're going to automate an attack against a single character of the password. Since we don't know the password, let's assume we don't know the password, we'll use the strategy of comparing all possible inputs. An easy way to do this might be to use something that we know can't be part of the valid password, as long as it is processed the same way. This will work just fine. So for now, let's just use a password as a null byte. We can compare the null byte to processing something else. This will plot a trace with an input of /x00, a null password. This is an invalid character and seems to be processed as any other invalid password. Let's make this a little more obvious and plot the difference between a known reference and every other capture. You need to write some code that does something like this. Reference trace is equal to capturing the password trace of an invalid character. For a character in list of valid characters, set the trace equal to a capture password trace of that character, and then plot the trace minus the reference trace. We may need to modify this a little bit, such as adding code to make a new figure, and also notice the above examples how I reduced the number of samples. Before the automating an attack against one character section, do we need to modify the first code block that is provided for us? Because we've had to modify most of the code blocks already. So I'm curious if we'll need to do the same thing here. So we'll probably be okay if we leave this code block. It already appears to contain the intended example code for generating the reference trace and comparing it to one valid character. This first block is for automating an attack against one character. It's a demonstration block, not one that we're going to add any code to. It already does the introductory comparison the notebook describes. It's going to show us the idea of using a null byte as a reference and visually comparing to another capture. Right. All right, so now we're going to want to make some modifications. Okay, great. Hopefully you now see one major difference. It should look something like this. Now we're going to move to the next cell block where we will make modifications. So this cell block, we should capture a reference trace using an invalid null byte, loop through all valid characters, capture each character trace, and compute the trace minus the reference trace of the invalid character, and then we'll plot the differences. This is the first real automation step after the example that we had just performed. So we're going to use a null byte as the invalid reference input. We're going to set the reference trace equal to your password trace of the null character. And we'll plot 1,000 samples. Next, we're going to define the valid password characters. Valid characters is going to be equal to A, B, C, D. I'm just going to copy string. Okay. Next, we're going to add new figure for plotting the trace, the differences between them. (14 by 6). Then we're going to call a for loop to traverse the valid characters. And for each valid character, we're going to set the trace. And that trace is going to represent each valid character. And we'll take 1,000 samples. We're going to set the difference between the trace, the reference trace, then we're going to plot difference and so after we traverse through all those valid characters and plot the difference between the valid character and the reference trace, the null character, also going to provide a title for our plot. We're going to call it difference traces relative to null byte reference. We're going to label the x-axis sample. The y-axis, we will label it as the power difference. And then we'll show the plot, run the code block, and hopefully it looks something like that. All right, so what we should do now is make this thing automatically detect those large differences. Some handy stuff that we can try out is the npSum and npABS absolute function. The first one will get us absolute values. Second one will get us the sum. It will add up all the numbers. So using something, let's see these code blocks here. Using just npSum means positive and negative differences will cancel out. So it is better to do something like npSum of the absolute difference to get a good number indicating how close the match was. So let's run this first code block just as an example of taking the sum. But this is taking the absolute value of each of these elements. This one is taking the sum of these elements. I don't think it's going to do anything. Copy data here. So let's take this, for example, take the sum here is that we used for the sum, and now we're going to take the absolute value before we take the sum. So we should get 16 because the negatives are negated. Taking the loop above that we had just used, we're going to modify it to print an indicator of how closely this matches our trace. Something like the following should work. Setting the reference trace equal to a capture password trace function call. So for each character in the list of valid characters, we're going to set the trace equal to the password capture trace of a valid character. And we're going to set the difference equal to the sum of the absolute value of the trace minus the invalid character trace. So the valid character trace minus the invalid character trace. The difference between those two, we're going to take the absolute value and then take the sum. And then we're going to print out the differences. So let's explore that next. So we're going to modify the code above to automatically print the correct password character. So let's comment out this raise statement. We're going to include our code modifications. We're going to import numpy NT. We're going to reference the invalid character, which is a null byte. Initialized is the password trace. And taking 1,000 samples. Next, we're going to initialize valid character array. And we're going to traverse the valid character array using our character counter identified as CH, and we're going to set the trace equal to the capture password trace. Again, the valid character plus a new line, and we're going to take 0 to 1,000 samples. Then we're going to set the difference equal to the trace minus the reference trace. We're going to set a difference variable equal to the sum of the absolute value of the difference trace. And then we're going to print the distance between the valid and invalid traces. We're going to execute that code. All right, so we have the results from that print statement. which prints the difference between the valid and the invalid characters that are used. So we see one very clear difference, one character that has a very clear difference when we run that loop. So we modified the code above to automatically print the correct password character. This should be done with a comparison of difference based on the printed characters. We should see one that is higher than the others. So my question of did we set a threshold here? We did not write a threshold yet. We're only printing the difference value for each character so we can see which one really stands out. So next we're going to finish this off. Rather than attacking a single character, we want to attack each character in the sequence. If we go back to the plotting of differences, we can try using the correct first character and wrong character. The basic idea is exactly the same as before, but now we loop through 5 times because there's 5 characters in the password that we're trying to decipher. And just build the password up based on brute forcing each character. We're going to take a look at the pseudocode that's provided, and then we're going to create some code that basically performs through this brute force method. So reading the first line of the pseudocode, we have a guessed password. That's going to be the where we store the password that we're guessing so far. So it's going to change as we iterate and we check for what character is the most appropriate and valid as we traverse through the characters that are valid, and we are able to compare. So we're going to loop 5 times for the maximum size, which is the maximum size 5, because that's how long our password is. We're going to initialize the reference trace to our guessed password plus the null character. And then we're going to traverse for each character in our valid characters array. We'll set the trace for each of these characters in the list of valid characters equal to a trace. We're going to capture it, and we're going to set the trace equal to whatever we capture. And it's going to be of the password that we're guessing and the character followed by a new line. We're also going to set the difference, which is going to be equal to the sum of the absolute value of the trace that we're capturing, subtracted by the reference trace, which is an invalid null byte character. And then we're going to compare at the end. If the difference is greater than the threshold, then that will be a more correct character. And then we're going to just print what the guessed password is at the end. So we're going to go ahead and add that code here. So we're going to explore how we can implement running a full attack on a password now. By building the password 1 character at a time. And the way we do this is by comparing each candidate trace against a reference trace made from the known good prefix plus a null byte. This full attack in the pseudocode basically tells us to keep running the guessed password, repeat for up to 5 characters, capture the reference trace, and set that equal to the guessed password plus the null byte character. Then test every valid character with a password trace, which includes the guessed password that is valid plus one of the valid characters that we're testing. So the code that we're implementing, we will import our plotting tool. or no, this is our NumPy tool, which allows us to take the sum and the absolute value. We're going to initialize the valid character array, and that will be equal to this string. Then we're going to initialize the guest password. And then we're going to add a threshold of the suggested 0.25. For character in, so for a value, so for character in a range of 5, which is the max word length, we're going to set the reference trace equal to the all of our capture password trace function with our valid guest password plus our known non-correct character, which is the null byte, and we'll take 1,000 samples out of from 0. We have a nested inside that traversal of each of the valid characters in our password. We're going to check each possible combination for each of those 5 characters. So for each character in the valid character array, we're going to enter the trace of our guest password plus the character that is the current character we're checking in our array, plus a new line character, and a sample of 1,000. We're then going to set the difference equal to the sum of absolute value of the trace minus the reference trace. And if the difference is greater than the threshold, our guest word is going to receive the character that we are currently looking at in our array. Of characters. So we are receiving the following output of all A's. So perhaps something is a little bit off here. Check that we update the reference trace using guest password in case you see Okay, so I set the threshold incorrectly. It should be 25.0, not 0.25. Okay, it looks like we are getting everything printing out correctly. All right, so we did it. All right, this is what we're having. Some common problems you might run into first. If you get an output which keeps guessing the first character, check that when you run this function inside the loop, you are updating the prefix of the password. For example, the old version of the code looked like this. Let's see, here's the prefix. The guessed password progressively grows with the known good start of the password. All right, so we had gone through this entire lab for power analysis for password bypass. And we have successfully worked through the entire notebook. So that is a success. We are going to wrap up for today's stream. Thank you for anyone who tuned in to watch. Hope you have a great one.